Hello, everyone. Do you have any questions? So have you all seen the first assignment? Do you have any questions? So if you don't have any questions now, but you do have questions later, make sure to post on the assignment forum so that everyone can get the same answers. It's a Jupyter notebook. So it opens as a text file, and you need to run it in the same way I do, right? So the way I do is, it will depend, as a function of what OS you use, but for me, I have to type Jupyter notebook, and then the name of the notebook. But I think it's, what is it? IPYNB, something like that. All right. So that's how I start it. And then this starts a small tab like this in your browser. So the expected format for your submission is a Jupyter notebook. Some of the answers that you will give are in Python. Some of them are in plain text. Well, now you can learn a new thing. Any other question? Okay, so today we're going to see dynamic programming. And the good thing about dynamic programming is that we have essentially already seen it. So, first a mention about the name dynamic programming. It's very confusing. It doesn't mean anything. It meant something at the time, but for us, it doesn't serve a purpose to try to understand why it's called dynamic programming, and it doesn't really help to know the name to understand what it does. So just accept that it's called dynamic programming, and we're going to see what it does now. And one way that we've seen already dynamic programming is in the divide and conquer procedures we've seen that require memoization. So what have we seen that requires memoization, and what does it mean to require memoization? So what is memoization? So in a divide and conquer procedure, you recursively divide the original problem into recursively smaller problems until you get to a base case. And then in some of the problems we've seen, you go left and you go right. Let's say you only have 2 subdivisions. And eventually, at some point of the branches, you're going to end up finding the same subproblem to solve. And then if you don't use memory, you're not going to realize that these are the same subproblems, and you're going to solve the same subproblem twice or more, which can lead to many inefficiencies. And in fact, we had seen that if you wanted to recursively compute the Fibonacci number for a given n, using a divide and conquer procedure, or just using a non-unique recursive call, then if you did not use memoization, you would end up redoing a lot of the computation. So you would essentially do exponentially many calls and exponentially many times the same computation. So we have already seen memoization, and memoization is one way to do dynamic programming, and there's another way. But first, so now that I've said that, let's talk about what dynamic programming is. So you have already seen dynamic programming in the online book, but it's not very well explained, right? They give you an example, but it's not clear what it is. So it's a method for solving optimization problems that you can express with a recursive function. And so a recursive function can be like the Fibonacci sequence, except that in the Fibonacci sequence, there's only one answer, right? It's the Fibonacci number. But if you have an optimization problem, many solutions can be acceptable or feasible, but you're really only looking for an optimal one. And what's a problem that we've seen that's like that? So we've seen the knapsack problem. So we're going to talk about the knapsack problem later. And at the time when we saw the knapsack problem, which was week 1, we had a brute force approach to solve the knapsack, which was quite terrible, right? Because if you have n items in the knapsack, the brute force approach would enumerate all 2 to the n subsets, possible subsets of items. So now we're going to see a dynamic approach, not just now, but a little bit later. So divide and conquer with memoization starts from the original problem you want to solve and then divides it into smaller subproblems that have the exact same structure, but with smaller data, so to speak. So, which means you can get closer to the base case or base cases as you recurse, right? And again, a base case is a case at which you don't need to recursively compute anything. You can just give the answer. And so divide and conquer with memoization is a top-down version of dynamic programming. So DP is just the acronym of dynamic programming. So that means you start from, if you represent the recursive calls as a tree, and in computer science we usually represent a tree as the root being at the top. So top-down means we go from the root, which is the original problem, to the leaves, which are the base cases. So with divide and conquer and memoization, again, we start from the original problem, we go to the leaves. But in fact, it's not just top-down usually, because it's top-down and then we go back to the top, right? Because a recursive call always, I mean, in these cases, we always have a return function. So it's not just going to the bottom. Every time we go to the bottom, we have to go back up. But we still call it top-down. But there's another way to do the same, which is bottom-up, right? If you already know the base cases, and you do already know that because when you write your code, you have to know the base cases. So if you already know the base cases, one thing you can do is only start at the base cases. So you don't do the top-down and down-top. You just do down-top, which is called bottom-up. somehow they decided that it would be too clear if they just used down top, so they decided to call that bottom up, but it's the same. And so when we do bottom up, what that essentially means is we compute the same as a divide and conquer with memoization would do, except we already know that we have to compute the leaves because they are the base cases. If we never get to the base cases, then we can never actually end the recursion. So we know we need to compute the base cases. And then we look at the recursive function we're using to code, and instead of saying, okay, I know how to go from a big problem to a smaller problem, we say, well, if I know one way, I know the other. I know how to go from a smaller sub-problem to a larger sub-problem. And so instead of constructing things from the top to the bottom, we construct things from the bottom to the top. And so we're going to see a bit more formalism about this with the following example. So we all remember the Fibonacci sequence. The recursive formula for the Fibonacci sequence is this. So if I give you an integer, a positive integer n, you can compute the nth Fibonacci number with this formula. And we had seen how to use memoization to save a lot of these calls, right? Because if you do top to bottom Fibonacci sequence, at every recursive call that is now the base case, you have to make 2 calls, and that leads to exponentially many calls, okay? And we had seen that memoization could save us all these calls so that we really only have a linear amount of computations to do. And now the question is, okay, suppose that I want to write a bottom-up function that doesn't recurse, right? It's just iteration. How do I use what I've previously seen for Fibonacci with divide and conquer and memoization to write a bottom-up approach instead of a top-to-bottom? So I also need to identify the base cases. So what are the base cases of the Fibonacci sequence? 0, 1, yeah. So that's easy. So I know that memory of 0 is 0. So mem is just where I store my stuff. Easy, okay? And now I know that I need to compute all the Fibonacci numbers from 0 to n. I already know that in advance, right? Unless you have a magic formula. If you want to compute the nth Fibonacci number, you have to compute the n minus 1th, n minus 2th, and so on. So I need to compute them, but I don't need to compute them in the reverse order. Actually, I need to compute them in the forward order. So this is what I'm doing here. Right here, I'm going to say, I already have the base cases here that I'm going to store directly. And here, I'm just going to write essentially this. Right? So essentially this is just, sorry. Okay. So how do I know that this is going to work? Right? So this is the bottom up, because this, I claim that I already know these values. I don't need to make a recursive call to compute them. And I'm saying, well, now I can just compute this using the bottom values. Okay? How do I know that I actually know these bottom values? Can you see in the code what guarantees that I know these values? Yeah, so the base case tells me, right, it's like proving something by induction in math, okay? You test for the smallest case, and then you test that if it works for one case, it works for the next case. So you can check that for I equal 2, this works, right? Because mem of 2 equals mem of 1 plus mem of 0. And I know these values. So I can build the next one at the top incrementally, at least for the base case. I mean, the base case in the induction sense, right? And then now I just need to prove that if I know every value till an index I, but not I can compute, no, suppose I know every value until index I, but not I, prove that I can compute value I. Well, if I know every value till index I, but not I, then this is known, and this is known, thus I can compute this, right? So that's how you would prove by induction that this works. So hopefully this works. Okay, let's try another value. Okay, and so this is quite fast. And if you were trying to do this with our naive divide and conquer without memoization, that would be slow. I mean, we would still be waiting, and in fact, we couldn't really wait. I mean, there probably would be just a crash that the maximum length or depth of recursion has been reached. Okay, so that's very fast. All right, so here there's n plus 1 states, right? What I call a state is the number of, essentially the number of things that I need to memorize. How many things do I need to memorize here? How many different values? Well, that's essentially dictated here, right? There's n plus 1 values that I need to remember. And my dynamic program will compute each value once, right? You get to it, you can compute it directly. So we do one computation per state. Again, a state is the number of things I need to memorize. So one computation per state, there's n plus 1 states. And how much does a computation take? What's the complexity of this thing? In big O of n. Big O of n? I'm just asking for one, sorry, what's the complexity of this thing is what I mean. That's big O of 1, yes. That's constant time. That's independent of n. So, and I know that I have that many states, okay? But I also see this here, right? That's just because I have to go through every state. But in some cases, it's not as easy to see that this is, the whole thing is big O of n. Okay? But you can usually decompose it into how many states are there and how much computation per state. And typically in dynamic programming, the amount of computation per state is reasonable, right? It's usually going to be big O of n, maybe big O of n squared if you're unlucky. And usually what kills you in dynamic programming is the number of states. So for some problems, the number of states is just humongous, and there's no way to express in dynamic programming exactly what you want to solve with polynomially many states. Right, so any question on this? So what is the size of the state space here? So I can answer that. Big O of n. And what is the overall time complexity? Big O of n. Okay, so is this clear? Okay, now, do you think any recursive function or equation like this can be as good whether I use the bottom-up or the top-down fashion? So here, I exactly use one computation, so big O of 1 in our case, per state. Okay? And here I know in advance that I'm going to need to compute every intermediate state. And if I changed this to, I don't know, whatever, this would still be a perfectly valid recursive equation that I could still solve by dp. But now if I used this bottom-up approach as it is, well, first I would need to provide a lot of base cases, but that's not the biggest problem. The biggest problem is that here I would compute every value of f, even though I may not need to compute every value of f. Right? If I ask you to compute, let's do something easier here. If this is my recursive function and I'm asking you to compute f for n equal 170, then you really only need to compute f of 0, f of 85, and that's it. Right? You really only need two values. And if you did a divide and conquer with memoization, that would be implicit, right? You would only call f of 170 once. Then you would call f of 0, that's going to be a base case. Then you would be calling f of 85 and f of 0. So in this case, the divide and conquer with memoization would be quite nice because there's a lot of holes between all the indices you are actually interested in. But the DP with bottom up would actually compute every single intermediate value of that f, even though we don't really care for them. So sometimes divide and conquer with memoization is better than the bottom up fashion. But a way to fix this could be to say, I'm going to do the top-down version and mark with like a Boolean all the values I'm actually interested in. And then I process everything. I actually do the computations bottom up every time I'm actually interested in the value. But that gets more complicated. So it's just to tell you that, yes, this is good. This is good for the regular Fibonacci sequence, because in the regular Fibonacci sequence, we need all the values. But you don't always need all the values. So then there may be a trade-off. Okay, and it's not clear, it's not easy to determine when one should be used against the other when there's intermediate values that you don't care about. But it's just for you to be aware of that. Okay, so this we've done. All right, so now let's just remember the knapsack problem. So in the knapsack problem, you have n items, and for each item, you have a weight W and a profit P. And now I'm asking you to select a subset of the items such that the total weight of the items is at most capital W and the profit is maximized. So here's an example. You have 5 items with profits 1, 3, 6, 8, 9, and you have the corresponding weights of 2, 3, 7, 8, 9. And let's say that capital W is equal to 14. What is the best subset and what is its profit? So just so everyone understands, I'm going to give you 1 minute to think about what the answer is, just so I can make sure that everyone understands what the problem is so we can continue. And so I'm just going to walk around, and you can ask me if you have questions. Would it be better with less light? Yeah, sorry, I did not realize that until I saw the screen from over there. Movie. Yeah. All right, so what is the value of the best solution here? If capital W is 14. All right, what's the value of one solution you found? Sorry? Just give me a number. 13. So 13, that's using this item and these two, right? So that does add up to 13. So, all right, let's just go on and assume that everyone understands what the problem is. I mean, if not, interrupt me now. And now we're going to code that function using dynamic programming and see if we do find that the optimal solution is of value 13. Okay. But now the question is, I knew already the Fibonacci sequence, and I knew how the recursive equation was written. So I didn't have to figure this out. But now here, I'm just giving you a formal question, right? But you don't have a recursive expression of what that can be. So before I can write something like, I did for Fibonacci like this, well, I need to know what that would look like. Okay, so how do I figure out, for this problem, and in general, how to write a recursive equation for a problem? So, again, this is important. And in fact, this is harder in general than writing the code itself. So, can you think of something, one way that we could express what we're looking for, which is a solution with maximum profit for the knapsack, using a recursive equation? So we know that both for divide and conquer with memoization and bottom-up DP, we need to have a base case, and we need to be able to build the general cases or the general subproblems on top of the base cases. Okay, so I think for this problem, it may help if we think about what is a base case. What is a sufficiently small subproblem of knapsack that I can answer optimally, for sure, and simply in terms of computation? So the reason we're asking this question is because if I give you all the items, you cannot just give me the answer directly, right? So because the problem is too complicated in its entirety, now we're asking, how small do you have to make the problem so that you can give me an answer without having to do much computation? So what is a simple base case? That is still a knapsack problem, but simple enough that I can solve it immediately. Or, using big O of n for, maybe not all the items, but a subset of the items. So find me a base case, and then we'll think about how I can use that base case to recursively build the general case. Okay, so again, well, this time maybe 5 minutes. Find me a base case. If you have a base case idea, either try to figure out what the recursion is, or ask me what I think about it, and then we can discuss it. And then after 5 minutes, we're going to try to think about all the solutions and what we need to continue with. Okay? So this is a hard question, but it's maybe the most important question I've asked so far, because if you can do that, then everything else should be within your reach. All the coding part should be easy. But modeling using DP can be hard, especially modeling efficiently. So take 5 minutes and try to solve this problem. And maybe you will, maybe you won't, but at least once we see the solution, you will have a good understanding for why this is a good solution. All right, go. So again, the question is, can you find a base case for the knapsack that we can answer directly? Right? What's a small enough sub-problem of knapsack that we can answer as a base case? All right, so should we proceed to the solution, or would you want to take 2 more minutes to think about it? Either is fine. So raise your hand if you want to think more about it. If there's many of you that want to think more about it, we can think more about it. Anyone? Okay, so let's see. So any idea? What's a simple base case? What is a trivial knapsack subproblem that I can solve? Or what's a trivial knapsack problem? Yeah, so if there's only one item in the knapsack, I can answer very easily. How do I answer the subproblem with the knapsack with only one item? Yeah, compare the weights, right? So again, I'm not sure it's written anywhere here. We're only looking at the 0-1 knapsack, which means every item can be taken 0 or 1 times, but not 2 or more. Right? There's a version of knapsack where you can take an item as many times as you want. Here it's just 0 or 1. And so if I only have one item, that's a problem I can solve, because I have the capacity of the knapsack, I know the capacity of the item, and I can assume that the profit is positive. So if I can take the item, then I should take it. Right? So the only way I can get a non-zero profit is if I'm taking the item. So if I can take it, I'm going to take it. And I know that's the optimal solution for the subproblem that only has one item. Right? So that's a simple base case. So I can answer the case with one item. And then, well, the case with 2 items is already not so clear, because I have to do some enumeration of some sort. But now the question is, so I'm going to ask a new question, but let's agree that the base case requires one item, so that's the index of one item. And I also need to know the weight of that item, and I also need to know how much space there is in the knapsack. Because in the base case, you can't actually suppose that all the knapsack capacity is unused. Because that means the base case only happens when no other item has been selected. But in fact, if you think about it in a divide and conquer with memoization procedure, you would go from the top to the bottom by selecting items, and you would arrive at the bottom, at the base case, already having selected some items. And the question would be, there is that much capacity left. You can pick the item at the leaf or not. Right? But maybe there is no more capacity for that item. So the base case needs to know one thing on top of the data of the original problem. It needs to know how much capacity we suppose there is left. Right? Because I need to know that to know whether I can add that last item to the other ones. So I need to know how much capacity there is. All right. So how many cases are there? So I'm going to write the answer here. Yeah, 2 cases. Okay, so the base case requires the leftover capacity to be answered. And so all the other cases also require the leftover capacity to be answered, because you can't go from a case to the base case and tell the base case the leftover capacity if the general case doesn't know what capacity is left. So the only way you can call the base case and provide the remaining capacity is if any general case actually keeps track of that leftover capacity. So if that's an information required at the base case, that's an information required at any case. Okay? So we haven't exactly defined what the general case was, but what we're saying is, if I need it in the base case, I need it in general. And I also need something else, which is the index of that item. I'll need to know which item I'm looking at in the base case. So I need an index. What does it mean to have an index in the general case? How can we say with one index what item has been selected or not selected? Or how can I say with one index, how can I describe fully the problem with a single index? Because one way to do it would be to say, I'm going to keep an array of n booleans and put true or false whether I've selected each item. And I can say this is my state space. I have a state space with an array of booleans. What would be the size of this state space? So I have an array of booleans. How many possible arrays of booleans are there for n booleans? 2 to the n, right? For size 1, there's true or false. For size 2, there's true, 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 false, false, true, false, false, and so on, right? So for n booleans, you have 2 to the n possible combinations of true and false. So I can perfectly describe the state of my knapsack with 2 to the n possibilities, right, with an array of booleans. But then what we said is that, well, if your state space has size 2 to the n or more, then you're going to need to go through every state, and so it's going to take at least 2 to the n operations, because you need to do at least one operation per state. So sure, you could describe the whole knapsack with an array of booleans, but that would mean we would not be doing much better than just the brute force approach that also requires 2 to the n operations. So the question is, how can you, if possible, describe the state of the knapsack with just one index and the leftover weight? So what can that index mean? How can you choose one index and let that describe where you currently are in your process of selecting items? You need to speak louder, sorry. Another array of what?
Another list.
That would contain what?
Well, whether the item is selected or not.
Isn't that the array that, or the list that would contain all the booleans, and there would be 2 to the n such arrays that we would need to go through? Yeah, that sounds like it. So one way I can say, here's an index, and this is where I am right now in the process of selecting items, is to say I have looked at all the items before that index, and I still have to look at all the items after that index. And I'm not saying which item I have picked or which I have not picked. What I'm saying is I am at index I. I have made some selection of items before index I. And with the items I've selected, there is that much capacity left. And I have a profit of that much. But it doesn't matter what the selection of item is, because to decide how to pick all the other items, the only thing I need to know is what is the leftover capacity, right? So one way to see that, let's see if I can start this up. Okay. Right, so suppose that this is my array representing all my items. So what I'm saying is, I'm going to have an item I that says, I've already looked whether I wanted to select these items. Already decided. Yeah? And then this is still, I'm deciding this one here, and this is still undecided. Okay? And the only thing I need to make the optimal decision for these leftover items is to know how much capacity I have left. Because, in fact, the profit I've been able to make in that part of the array is irrelevant. If I know how much capacity I have left, I know that I'm going to try to make as much profit with these items as I can, independent of how much profit has been made here. Right? So the profit doesn't matter in deciding which items I select next. I'm going to, no matter how much profit has been made, I'm going to try to make as much as I can with what's left. So, and then one way to see this is that, so here what I've said is that I'm going to start at the first item, and then I'm going to list, depending on every capacity, whether I can take the item or not. And then I can keep doing that for the second item. And another way, so this may not be very clear yet, and I'm going to present another way of seeing this first before making everything clear. One thing I can always do is say, I'm going to cut my array in two. And here I'm saying, I'm going to use half of the capacity for this array and half of the capacity for this array. And I can recurse. But in fact, I don't always have to use half of the capacity in every side. Maybe the optimal solution could be, I'm going to not take any item and say that 0 capacity is allocated to these items, and all the capacity is allocated to these items. But in fact, it could also be 1 and W minus 1, or 2 W minus 2, and it could be W minus 1 and 1, or W and 0, right? Any of these allocations of capacity to any partition of my items could lead to an optimal solution. And so I have right, and so here I said I cut in the middle, but in fact you could do exactly the same if you said, well, this is not a very good rubber. In fact, you could say, I'm going to do the same for the first item. What if I allocate W over 2 for the first item and W over 2 for all the other items? That could lead to an optimal solution. In any of these cases, sorry, but you haven't been able to see what I was written and nobody complained. Sorry. So, right, any of these allocations could be valid and could lead to an optimal solution. And I can actually list them all. Right? And there's n plus 1 of them, or W plus 1 of them. Okay, so this justifies what we have been saying so far. And because it's time, I'm going to let you go, but we're going to resume tomorrow. Oh, wow, that's pretty drastic. Oh, okay, no, sorry. I think my computer is actually deciding to quit. So that sounds like a good sign. We're going to stop here. And we're going to finish to solve the mystery of dynamic programming and knapsack tomorrow.